Here we have discussion about electric dipole and flux line. So what is the dipole? So when the charge plus Q and charge minus Q are separated by some distance, that forms the dipole. Okay. So the dipole is formed when 2 point charges of equal magnitudes and having opposite sign. So here you see that we have plus Q and minus Q and separated by distance d. So it forms the dipole. When this dipole, if you take that, sometimes we have permanent and sometimes depends upon the electric field also, we have different orientation. So now in this case, we are trying to define the dipole moment. So the dipole moment is the product of the charge and the distance between two charges. So that is P equal to Q into D. Next, we are going to define what is the flux line. So here we are talking about the electrostatics. So we are talking about the electric flux line. So that is the imaginary path or line so that it has a direction at any point will be the direction of the electric field at that point. So that imaginary path or line, like here, if you see that, so at any point, suppose we are going to consider here, it will have same direction at the direction of the electric field. So that is called as the electric flux line. And if this particular circle you can see here, or we can have a concept of the sphere, when they are equidistant from the charge, then it has same equipotential surface. Next, we have discussion about the energy density. So in particular volume, we are trying to calculate that how much energy density is there. So first we'll see in case of point charge. So to understand the energy density, first we are trying to calculate the amount of work to bring those charges in particular volume. So here in case of point charge, we have considered that charge is located at the infinity and that charges we are trying to bring into the particular volume. So now when this is the empty, here nothing is there in the initial situation. Okay, so when we try to bring the charge Q1 along to the point P1, so Q1 will not feel any resistance. Okay, so in that case, work done is 0. Okay, that is represented here by W1, so that is 0. Now, once we'll try to bring the charge Q2 from the infinity to the point P2, so now since already it has charge Q1, so that Q1 is going to produce some effect on this. Okay, so that we have to calculate the potential due to charge Q1 on charge Q2. So that potential is represented here by B21. Similarly, when we try to transfer the charge Q3 from the infinity to the point P3, it will have potential that is faced by the charge Q1 as well as Q2 both. Okay, so that's why it's written here B32 plus B31 due to charge 2 on charge 3 due to charge 1 on charge 3. Now, if you see that in this case, total work done, so that is W1 plus W2 plus W3. So in case of W1 value is 0, W2 is Q2 into B21, and for the Q3, that is the W3, we have Q3 into V31 plus V32. Since that time, charge Q1 as well as charge Q2 both was available. Now, if you want to reverse the situation that, now we'll try to bring the charge Q3 first to the particular position, point P3. So now, since nothing is available in this volume, so Q3 will not face any resistance here. So that work done is going to be 0. Now charge Q2 will try to bring here. So in that situation, already Q3 is there. So that's why it's written B23. Okay, due to charge 3 on charge Q2. So similarly, once we'll try to bring the Q1 here, so that time already charge Q2 and Q3 is available. Due to that, that work done is Q1 into V12 plus V13. Now we'll add this equation 1 and 2, both equation we are going to add here. So if you see that in situation, then finally we are 2WE Q1 into, this is the due to charge 2 and charge 3, and this is the charge 1 due to charge 3 on the charge Q2, and finally this expression is due to charge Q1 and Q2 on charge Q3. So finally this B1 plus B2, B12 plus B13 is written as the B1, B21 plus B23 is written as the B2, and B31 plus B32 is written as the B3. That is the potential at Q1, potential at Q2, and potential at Q3. So already we have discussion about this potential earlier. Okay. So that potential was defined. Okay. What was the potential? So that work done to bring the unit charge. Okay. That was the potential. So now finally, this one we can summarize. So this one we consider only for the 3 charges. It can be for the n point charges. So in that case, we are using 1/2 summation. Okay. So here this WE came and this 1, 2 was left side, that we brought the right side. That's why we got here 1/2. So now finally equal to 1/2 summation K equal to 1 to N, and its product of Qk into Vk, that is given the joules. So this is the condition in case of point charge. Now if we discuss in case of continuous charge distribution, so only what we have to find the value of the charge here. So in case of line charge distribution, charge density is the rho L, length is L. So this charge is going to become the rho L into L. Now we are considering the differential length, then this is the rho L into dl. So that's why we are going to integrate over this. In case of surface charge density, rho S is the charge density and differential surface is the ds. So we are going to find the integration of this one. In case of volume charge density, rho V is the volume charge density and differential volume is the dV. So finally we have total work in this case, half integral over the volume rho V into V into dV. So B is the potential here, okay? This B is the potential. Now, by using the Maxwell equation, already we have expression rho V equal to, what's the value? Del dot D. So that expression we are going to use here. In place of rho B, we have substituted del dot D. Now in this, we are going to apply one identity. So on the basis of that identity here, you can see that if A is the vector quantity and V is the scalar quantity, then del dot VA equal to A dot del V plus B into del dot A. Now we are trying to rearrange this equation since we have del dot vector quantity into a scalar quantity. So that is the del dot VA minus A dot del V. So finally, by using equation 8 and 9, so means we are going to substitute the value of equation 9 and equation 8 in terms of where A is for us, that is the flux density, and V is for us potential, that is the V only. So finally, it has 2 parts, okay? One is the first term, another is the second term. Now here if you see that by the expression of the potential or by the expression of the flux density also. So flux density is what? That is the epsilon naught into E. And what is the value of electric field? That is the Q by 4 pi epsilon naught R square. So this epsilon naught will be cancelled. Then also flux density is proportional to 1 by R square. And whereas we know about this potential, so that is equal to how much? Q by 4 pi epsilon naught into R. So it is proportional to 1 by R. So like this here, V is going to change as 1 by R, D is going to change as 1 by R square in case of point charges. And in case of dipole, B is going to change as 1 by R square, and this flux density is going to change 1 by R cube, and so on. So finally, what you are seeing that at least product of potential and flux density is going to change by 1 by R cube. Okay. So while this differential surface area is going to vary as R square. So in that situation, that integral of the first term of the equation 10. Okay, this first term is going to become 0 since surface is going to be very large. So now finally, so that first term becomes 0. So equation 10 can be written as here, W equal to minus 1 by 2 integral over the volume d dot del V into dV. And now already we have this expression, okay, relation of the E equal to minus del V. So that value is substituted here. So minus minus become positive. And another expression we have D equal to epsilon naught into E. So finally, work done is what here? That is 1 by 2 volume integral epsilon naught E square into dV. So now in case of electrostatic energy density, if you try to find, that is the joule per cubic meter. So for that, we are dividing this one, okay, with the differential volume. So finally it's become 1 by 2 dE. And here again, d value is substituted. D is epsilon naught into E. So finally we have d square by 2 epsilon naught. Now, if you try to find in the general way, what is the total work done? So that one, this electrostatic energy density is being integrated over the volume. So now we'll try to see one small numerical to check our concept to our understanding. So in this, what is the situation? We have 2 point, not two, we have 3 point charges here. One is the minus 1 nanocoulombs, 4 nanocoulombs, 3 nanocoulombs. So that nano will be 10 to power minus 9. So those charges are located at, location is given. These are the coordinates 0, 0, 0 for the first charge. Okay, suppose this is the Q1, this is the Q2, this is the Q3. For Q2, it is 0, 0, 1, and for Q3, it is 1, 0, 0. So finally, total work done is here, okay, that we are trying to find, same as the previous situation. So initially we are trying to bring the minus 1 nanocoulomb charge to the system, so that work done is here 0. And for the when we're trying to bring the Q2, okay, so that is Q2 into B21, and we try to bring the Q3, so already Q1 Q2 is available. Due to that, we have Q3 into B31 plus B32. So now here, this is the expression for the potential due to charge Q1. So Q1 by 4 pi epsilon naught, and here we have R, that is the where we are trying to find. In that situation, we have to find these values. So this expression is here, the point, okay, with respect to that point. So here location of the Q2. This is the location of the Q2. We have formula R minus RK. So now we are finding for the, in case of, this is the due to Q1. So that location we need to find. So we are finding where? To the charge Q2. So that's why here we have position vector of charge Q2 and position vector of the charge 1. So that modulus. Similarly here, we are finding on Q3 due to Q1. So final position is the R3 and due to Q1, so R1. Here again on Q3 due to Q2. So we have modulus of R3 minus R2. So we have subtracted the concerned coordinates from each other. So finally we have here 1 in the denominator and here in the second also 1. In last one you will get here 1 comma minus 1. So finally modulus of this 1 square plus 1 square. So root of this is what? Root 2. And now we'll substitute the value. So Q1 into Q2. So that is going to become minus 4. And 10 to power minus 9 into 10 to power minus 9 become 10 to power minus 18. Similarly, Q1 into Q3. So minus 1 into 3. So that is the minus 3 and 10 to power minus 18. Last one we have 4 into 3, that is 12, and 10 to power minus 18. So now we have to substitute all values, and after simplification, epsilon naught value, we know that it is the 10 to power minus 9 by 36 pi. So once we substitute this value, so this is the 13.37 nanojoules. So like this, we are able to find the energy density, and we can understand here what is the flux, as well as we have discussion about the dipole. Okay, keep watching.